Hello everybody, welcome back. Today we will start looking at statistical inference. The first kind of inference that we will look at is called confidence interval. So let's say that we have a target population and we want to estimate a certain parameter for that population. So the parameter could be population mean of some variable, let's say height, and it could be proportion, it could be standard deviation, variance, things like that. So, just think for now that the parameter is the mean of a population mean of some variable like height. And so to estimate the population parameter, we take a sample and we calculate a corresponding sample statistic, and so the sample statistic would be, let's say, the sample mean of height. So the sample statistic is used as an approximation to the population parameter, and also the sample statistic is used to make inferences about the population parameter. We will first focus on confidence interval for the mean of a population. We will look at confidence intervals for proportion or variance at a later time. Okay, so the goal of the video is to use sample mean x bar to estimate the population mean mu. And to have an example in mind, I'm going to state the following example. Let's say that we want to determine the mean height of BGSU students, and let x be the height of let x be the variable that denotes the height of a student. So let's say to determine the to estimate the mean height of BGSU students, we take a sample of students and take the measurements of height for those students. So here the population of units would be all the BGSU students, and we take a sample of, let's say, 16 students and look at their height, look at the measurements of their height. And so let's say this is the sample that we get. So again, the height, we are using inches as the unit of length. So all these measurements are in inches. And so we want to obtain a point estimate of the mean height mu, and the sample mean here. So if I calculate the average or mean of these sample measurements, then we get lowercase x bar equal to 69.375. So this is our point estimate for the mean height of BGSU students. Now, if we tell somebody, hey, this is our estimate for the mean height of BGSU students, the very immediate question they will ask is what is your error of estimation? So again, 69.375 or X bar is to estimate the mean height, and the immediate questions that arise is how good is your point estimate, and how would you quantify the error of estimation, and what is your confidence level in your estimation? So if we are using small x bar, the sample mean, the observed sample mean, as an estimation to the population mean mu, then the error of estimation is x. The error of estimation is how far away the population mean is from x bar. So basically, you look at the distance between x bar and mu, right? Which is basically x bar minus mu in absolute value, let's say. So this is the error. Now we won't be able to say anything deterministic about this error, and so the question then is what can we can we say something probabilistic about the error of estimation? So that would be our focus. So here is so in order to answer these questions, so again we want to use sample mean to estimate the population mean. In particular, in our example, we want to use sample mean height as an estimation of population mean height. And the gist of how we are going to answer these questions is the following. So what we're going to do is we will develop a procedure to create an interval of values centered at the sample mean, that is a range of values centered at the sample mean, so that 95% of all samples will produce such an interval that will contain the population mean mu. So again, we will develop a procedure to create an interval centered at the sample mean, or that is the range of values centered at the sample mean. Such a range of values or interval will be called a confidence interval. And our procedure would be such that 95% of all samples will produce confidence intervals that will contain the actual population mean. So that is, if we take samples repeatedly and compute sample mean repeatedly for each sample that we obtain, then 95% of all samples will produce a sample mean and a confidence interval that will contain the population mean mu. All right, so you may not understand exactly what I mean, what I mean by what I just said. So as we put in more details, it's going to make more sense. So there are two cases. One is there are two cases to look at. One is that we know the standard deviation of the population, that is sigma. Sigma, one case is sigma is known, So in our example of BGSU students and their height, so sigma would be the standard deviation of height for the entire population. And we're going to assume that we know that. The other case would be obviously that sigma is not known, in which case we are going to have to estimate the population standard deviation by using a sample standard deviation. And we're going to look at the case when sigma is not known in a later video. So assuming that sigma is known, then recall that the sampling distribution of x bar is normal with mean equal to the population mean and variance equal to the variance of the population over the sample size. Now this is true when n is large, and this is always true when the population has a normal distribution approximately. So the first step in our inference then is the assumption that the sampling distribution of x bar is normal with the mean equal to the population mean and standard deviation equal to the standard deviation of the population over the root of the sample size. Okay, so remember again, the goal is to create a confidence interval, right? That is an interval centered at the sample mean, a range of values centered at the sample mean. So the first thing we're going to do, so we make this assumption that x bar has normal distribution. So then the first thing I'm going to do is the following. So this is the distribution of x bar, and so the mean mu is the mean of x bar as well. So the mean is exactly at the center of the normal distribution. Now we want to find a number m, small m, such that so we want to find m so that the probability that x bar is between mu minus m and mu plus m is 95%. So this is the probability that x bar is m units from the mean mu. And so we want to find m so that the probability that x bar is m units from the mean mu is 95%. Now, what is the meaning of this probability right here? What does this probability mean? So what is the random experiment here? The random experiment here is that you take a sample of size. Remember, we fixed the sample size to 16. So you pick a sample of size 16, and then you compute the sample mean x bar, and that's the experiment. So the outcome of the experiment, we were saying the probability that the outcome is in this range is 95%. So that means if we carry out the experiment repeatedly, right? So take a sample, calculate the sample mean, right? If that experiment is calculated, if that experiment is carried out repeatedly, then the proportion of times the sample mean will be in this range is 95%. So 95% is the proportion of proportion of samples for which the sample mean will be m units from the population mean mu. So again, 95% here is the proportion of samples for which the sample mean will be m units from the population mean mu. So 95% of all samples will produce a sample mean that is within m units from the population mean mu. So again, so that's what we want to find. We want to find m so that this probability is 95%. Okay, so how do we find that m? Well, I'm going to take help from the z-score of x bar. So what is the z-score of x bar? So the z-score of x bar is given by this formula. So z is x bar minus the population mean over the standard deviation of x bar, which is sigma over root of n. And we know that the z-score has standard normal distribution. Now from this equation, we can find that x bar is z times sigma root of n plus mu. So mu plus z times sigma over root of n is equal to x bar. So these two equations are equivalent. And so again, remember, my goal is to find an m so that the probability that x bar is m units from the population mean is that. So instead of finding this first, I'm going to first find we're going to first find an m. So to find an m, so we're going to first find the z-score z star, so that the probability that the z-score is between negative z star and positive z star is 95%. And we can use the standard normal distribution table or any software calculator or Desmos, whichever you like, to find that the z star is 1.96. So notice that the area to the left of z star would be 97.25. So again, we first find the z-score z star so that the probability that z between negative z star and positive z star is 95%. In other words, we want to find a z star so that 95% of the standard normal probability, so that 95% of the area below the standard normal curve is between negative z star and positive z star, and and that z star has to be 1.96. So we found that if z star is 1.96, then 95% of the area below the standard normal curve lies between negative z star and positive z star. So negative 1.6 and positive 1.6. So now compare this and the distribution of x bar. So we know that the probability that, so we want to find m so that the probability that x bar is m units from the population mean is 95%, and we just found out that the probability that the z-score is between negative 1.96 and positive 1.96 is also 95%. Now, so the mu plus m, right? This is a value of x bar, and that value has z-score 1.96. So the z-score of this value of x bar is 1.96. So from the formula for the z-score, so this is the formula for the z-score, which can be rewritten as this, as we said, and the value of x bar we're going to pick is mu plus m, and so again mu plus m has z-score 1.96. So mu plus m here, x bar will be replaced with mu plus m, and z will be replaced with 1.96 because mu plus m corresponds to this z-score. So then from this equation we see that m has to be, because mu cancels out from both sides, and we find that m is 1.96 times sigma over root of n. So we found the quantity m that we wanted. So again, we found m so that the probability that x bar is m units from the population mean is 95%. So we found that m, And this m is called the 95% margin of error. So again, what is the meaning of that? So that means that the probability that x bar is m units from the population mean is 95%. So we found that it is 95% if and only if m is 1.96 times sigma over root of n. And I haven't plugged in the values of sigma and n yet for our BGSU students' height example. Now this probability then is, because m is this value, now I can say that the probability that x bar is between mu plus 1.96 times sigma over root of n and mu minus 1.96 times sigma over root of n. That is, the probability that x bar is this many units from the population mean is 95%. Now this set of inequalities here is equivalent algebraically to the set of inequalities here. That is, we can rewrite this set of inequalities in this way. That is, that the mean population mean is bigger than x bar minus 1.96 times sigma over root of n and less than x bar plus 1.96 times sigma over root of n. And the probability of this of the event that the population mean is in this range is 95%. So what is the meaning of this probability right here? So what it means is that if we take samples repeatedly and compute sample mean repeatedly, then the 95% of samples of size n will produce a mean x bar and an interval from x bar minus the 95% margin of error to x bar plus the 95% margin of error that contains the population mean mu. So to make it concrete, the 95% margin of error is defined to be the value m equal to 1.96 sigma over root of n, and the 95% confidence interval is an interval of the form x bar minus the 95% margin of error, comma x bar plus 1.96 x bar plus 95% margin of error. So this is the range of values centered at x bar. The population mean mu will be within 95% margin of error of the sample mean for 95% of the samples. Okay, so that's the general discussion on the. So this is the. So what I want to do now is basically go back to our example. So you remember in our example, n, we took a sample of size 16, so n is 16, and we're going to assume, so going back to the BGSU students and looking at trying to determine the mean height of the students, we took a sample of size 16, and we're going to go ahead and assume that the standard deviation of height for the entire population is about 2.8. And remember that we calculated the sample mean to be 69.375. So the 95% confidence interval for our example would be x bar plus or minus 1.96 times sigma over root of n, and sigma would be 2.8, n would be 16, and so we plug that in. So we get 69.375 plus or minus this quantity would be 1.372. So this is the 95% margin of error. And so 69.375 plus 1.372 is 70.747. 69.375 minus 1.372 would be 68.003. So So the 95% confidence interval is the interval from 68.003 to 70.747. Our confidence level is 95% in stating that the population mean is in between these two values. So again, the reasoning here is that the confidence interval that we picked, we are not saying that this specific interval will contain the population mean with 95% probability. What we are saying is that if we calculated a confidence interval in this way for many different samples, then 95% of the time the population mean will be in the corresponding confidence interval. So to find a confidence interval, the first thing we need to do is find the sample mean. So we have to take a sample, find the sample mean, and so find the sample mean and then set confidence level. So throughout my discussion, I set my confidence level at 95%. So we calculated a 95% margin of error and 95% confidence interval. But a lot of the times you can also set the confidence level to 80%, 90%, or even 99%. But 95% is basically the standard confidence level, and then you want to find the level C margin of error M, and once you find the level C margin of error, the level C confidence interval would be given by the lower limit for the interval would be x bar minus M, and the upper limit for the interval would be x bar plus M. Okay, so let me just now look at the z-score corresponding to the confidence level C. So if the confidence level is set to 80%, in that case, the z-star would be 1.282. So that is 80% of the area below the standard normal curve will be between negative 1.282 and positive 1.282. And the 90%, if we set the confidence level to 90%, then the z-star would be 1.645. And if we already saw that if we set the confidence level to 95%, then z-star would be 1.96. And if we set confidence level to 99%, then z-star would be 2.576. Again, this means that 99% of the area below the standard normal curve is between negative 2.576 and positive 2.576. So here is the table that gives us, so this is the first row gives us the confidence coefficient or confidence level, 80%, 90%, 95%, 99%, and the corresponding z-star values. And so once again, whatever the level C is, confidence level C is, it's usually one of these four. Whatever the level C is, we want to find level C margin of error, and the level C margin of error M is given by Z star times sigma over root of n. Now sigma over root of n is the standard deviation of x bar, or it is the population standard deviation over the root of the sample size. And so this is basically the margin of error is the width of the confidence interval, and the confidence interval is given by x bar plus or minus m. Okay, so we're going to look at the case when sigma is unknown in a later video. So I'm going to stop my discussion here right now, and do some more examples in the next few videos. See you then.